So today we are going to start taking us through what we call a tour of selected machine learning algorithms. So alhamdulillah, so far we cover several concepts. So we want to start looking at, when we talk of machine learning, there are a couple of algorithms or several of them that are behind this unique capability that we expose some set of data sets to the system. And then after enough of training, the system gets to be able to recognize unseen data. So how does it work? What is the brain behind it? So is it just like that? A colleague once witnessed a very unique, excellent prediction. He couldn't imagine it. He said, "Is it a magic?" I said, "No, it's not a magic. This is just the work of machine learning algorithms." So if the problem is very simple, you can get a very simple algorithm that can solve the problem for you. But sometimes the problem gets complicated and you might not be able to get a single machine learning algorithm to do the job. So we go further to what we call ensemble, where you try to combine more than one or two or as many as possible machine learning algorithm together in a kind of cooperative and competitive manner in what we call ensemble. And already we cover some of these concepts. So today we're going to we introduce ourselves to the concept of machine learning algorithm. Especially we are going to be focusing initially at the classification. As you know, in the supervised learning, we have classification, we have regression. Classification is when you want to predict classes, like you want to determine if somebody is going to pass an exam or is not going to pass. That's like yes or no. You want to predict if somebody is having a particular disease. Is it diabetes or non-diabetes? These are called classification problems. And the other one is called regression, in which case you want to train your model you want to develop a model to be able to predict what is the age of an individual. You know, maybe there are in some criminal investigation, you want to investigate the particular kind of samples that have been found in a particular site. We want to estimate the age of such individual. So how do you do that? This is regression. You want to predict the amount of the percentage of corrosion that will take place after some time. To the civil engineer, this is also a regression problem and also several other regression problems. However, classification and regression, as we are going to link each and every one of them later on, and we're going to take them one after the other, often it's easier to come with classification compared to regression. That's why most algorithms start off with classification. Then later they extend it to handle regression. For example, the popular support vector machine was initially dedicated to classification problem, two-class problem. And then later it has been extended to the concept of regression problem solving. So this is what we want to introduce ourselves to. Then thereafter, we're going to pick a couple of algorithms, samples of them, because there are so many algorithms. We're going to pick samples of them. We'll start with a very simple one that everybody can have, hopefully, better understanding. Then we move on to more complicated options. Now, to remind us, to remember in our general framework for machine learning. So this is a kind of a review. You have your data. Always remember our principle, the principle of machine learning, which is let the data speak. It means that the data will determine the kind of performance your model could get. No matter how powerful an algorithm is, if the data is really, really bad, you might not be able to get anything. And that's why we say there's no algorithm that is better than every other one. So I used to have this aphorism. If you talk to someone, you say, oh, this algorithm is the best. We don't have best algorithm. It depends on the data set. An algorithm today could perform the best or achieve the best result. Tomorrow you bring another data set, it could go down to the bottom, not able to even recognize the system. So it depends on the data. That's why we say in machine learning or data science or data analytics, we say, let the data speak. So before you ask me if I'm going to get accurate results in this problem, I say, bring your data. Your data will determine what we are going to. Of course, we can try to use simple algorithm, complex algorithm. In fact, sometimes one of the principles also we have introduced ourselves to and we have to take note is, it's always recommended to start with simple algorithm in machine learning. Start from simple algorithm, then you keep increasing the complexity as you go on. Otherwise, if you go start with very complicated algorithm, you might miss the simple underlying properties of the data set. That's why we have seen simple algorithms sometimes performing better than more complex algorithm because the nature of that data set. So you start from simple algorithm. If it fails to recognize the relationship within the data set, then you move to little more complicated until you go to even more complicated one. And if no single algorithm can give us what we need, then we move to hybridization, combining two methods or try to let multiple methods combine together to predict and then vote on what is going to be the final result, which we can find some of our videos in the channel regarding the ensemble model and some examples. So once you get your data, you explore the data exploration. You could try to visualize your data. Visualization can help you in several ways. So by visualizing data appropriately, you'll be able to see if this data is, if the data set is having outlier or noisy data, so many other things you can get from there. Sometimes also we might have to go for feature selection, feature extraction. Some data are just raw. Raw data could be given to you by the client. You have to find out what are the features from this data, especially for people dealing with images. They just send you images, so you have to find a way of automatically extracting features from those images. You might have to even bypass human intervention sometimes. Let the system detect which image feature will be appropriate. So then once you got this thing ready, your data is ready to go into the learning stage or modeling stage, then this is where we are here. You have the learning process. To have learning, before learning can take place, you need to have the appropriate algorithm. So, and the foremost of the type here is called the supervised learning. We have supervised learning, unsupervised learning. As we described in the introduction to machine learning, we can also see the videos on our sites. But for the supervised learning we are taking presently, so supervised learning is where you are going to expose your data set, your algorithm to two types of data. We have the training set, which is very important. So in the training set, you are going to have the input and the output. You'll be showing the two to your system. This is my input, this is the output. For example, this is this patient number one's data. This patient is diabetes. Patient number two, this is the data. It's not diabetes. You keep showing it, the system tries to understand what is making the first person to be diabetes, why the second person is not diabetes. This is called the training process. Once the training is done completely, then we have a reserved portion of our data, which we call the testing set or validation set, as the case may be. So we also have the input and also the output, but we're going to keep the output away from our system. Then we give the input to the model that has been produced after training. That, okay, Bill, can you check if you can understand this sample? Is it diabetes or non-diabetes? So this is the training testing process that's usually carried out. Another, this supervised learning, we have two types. We have the regression, I just mentioned them, where you are predicting real numbers. Now you want to predict the age, you want to predict in a single problem from maybe a client could give you a particular problem to solve. You can have multiple problems. I call it multi-stage predictive solution. If somebody asked me to predict student performance, I might want to start by predicting, by having a classification problem, which is the student going to pass or fail? That problem is a classification problem. Is he going to pass or fail? The next stage is, okay, if I say the student is going to pass, what is going to be the grade of the student? Is it going to get A or A plus or B plus or C plus? That is multi-class problem. Multi-class problem. The first one is classification problem, but two-class problem. We call it binary classification problem, which is usually the easier one to do. Because the more the number of classes, the more complicated it becomes. So when I want to predict the actual grade is going to take, like, it's going to get A plus, B plus, it becomes multi-class problem. So it means we are moving from, we started from binary classification to multi-class. Multi-class. They are both, all of them are classification problem. They are all that is. Then the second one is the regression. This is the one we explained. The regression is where, for example, now I want to predict the actual score of the student in the final exam. I want to predict the actual score of the student in the final exam, maybe out of 40%. Is it going to score 30% or 35.6? This is known as regression problem. So you're trying to predict actual values. So these two come under the supervised learning. But for now, we are starting with classification problem first. Because like I said earlier, it's easier for especially newcomers or people who are new to machine learning to easily grasp the basics of classification compared to regression. And that is actually the normal sort of things when we deal with classification and classification or regression. Majority of algorithms start off with classification. Later, they can extend it to cover regression. We recognize this. So where we say we want to cover, of course, with this curve evaluation we follow, we go to evaluate the model to see is it doing fine or it's not doing fine. And then finally, you have your model will be generated at the end of the day. So once this model is generated, then you can then use it subsequently for whatever predictive prediction you want to use it for. So we also already discussed how do you evaluate models, discussed this extensively with several videos on that. So how you can check if your model is performing well, is it overfitting, is it underfitting, and also of others. But like we said, now it's time to really go into how is the process of classification using those algorithms going to take place exactly. Now, when we talk of classification, so we say classification is a data science task of predicting the value of categorical variables, which we often call target classes. The target class could be anything. You want to predict if your student is going to pass or fail. You want to predict if there's going to be rain or not. There's not going to be rain. That is a classification problem. So we do that by building a model based on one or more numerical categorical variables, which we call the predictors. Now, since our intent is to discuss algorithms this time around, we have different types of classification algorithms. See, the main group of them, they are grouped into 4 groups, basically. So we have the frequency table-based algorithms. That is, they're based on frequency table. So that you have to prepare frequency table, just like in statistics. You have data set, you have the frequency table. From the frequency table, we can figure out what is the solution to this. So on the frequency table-based one, we have the 0R method, the 1R method, the naive Bayesian, and the decision tree. These two are very, very popular and they have been used a lot. They have demonstrated a lot of unique capability. So we are going to be looking at them as samples later on. The other one is covariance matrix-based algorithms. So which are classification algorithms that are based on covariance matrix principle. So we have the linear discriminant analysis in this group and the logistic regression as an example. We also have the similarity function-based algorithms. So the popular example in this sense is the k-nearest neighbor. The k-nearest neighbor, which usually come to mind quickly when you talk of classification algorithms. Very popular, simple, easy for anybody to quickly understand what is going on. And we have the group of others. Other means there are so many different kind of underlying principles that are used to build them. So we say others. These 3 are unique. Why this one? There are so many methods that we use to build this different algorithm. For example, we have the neural network that was modeled after the working of the human brain, the neural system in the body. We have support vector machine, which is basically a statistical modeling algorithm. So each of we are going to see as examples later on as we move on. Inshallah. Now, consider the list of classifiers. See, there are so many classifiers these days you can talk of. So classifiers, they are algorithms that are used for classification process. So we have the k-nearest neighbor, usually one of the unique favorite for newcomers to quickly pick because the working is very simple. We have the naive Bayes, we have the decision tree, we have support vector machine, artificial neural network, logistic regression, and host of others, many as possible. As many as possible. So the list is unexhaustible. The question someone asked me was, which one is better in this algorithm? And like I said, there's no one that is better. You cannot just say an algorithm is better. You always tell the person that it depends on the data set. That's why this principle must always be with us. Let the data speak. So what we only using the algorithm to do is to understand what the data is saying. Every data set is speaking some stuff. It's having some messages to be passed across, but we cannot understand those messages. So sometimes you see k-nearest neighbor might be able to understand the message of that data set. Next time you might bring another data set, the message is too complicated for k-nearest neighbor. He couldn't figure it out. It could be another time, it could be neural network that will perform excellently well. So no algorithm is always better in our situation. We have to take this. That's what someone said, this is a big challenge in machine learning. I say, yes, that's the big challenge. Because it wants a particular algorithm that I can just develop and use for every problem. I say it doesn't happen even the principle of artificial intelligence is against that, actually. One of the unique attributes of artificial intelligence is you use it in a restricted domain, in a particular domain. You see, you don't develop an artificial intelligence system that will solve all problems. It's too complicated. It will be too complicated to handle. We have to take note of this. Saying, therefore, which algorithm is better? It's not even a question. So because it will not be, there's no answer for that this is better. So it depends on the problem you're solving. That's why you have to expose your data set to different algorithms and then go with the one that is better. And that is why comparative analysis is very common in machine learning research. Because the idea is you want to be able to research and find out which algorithm is better for this particular area. Maybe in oil and gas, there could be some algorithms that are very good at modeling such data set. Even yet, they keep competing with themselves. So now, in a basic example of how the classification works, so let's look at this simple example before we move to the algorithms themselves fully. So let's say you have data sets given to you. So these are the grades. You get the CS grade of 5. It is the output is fail. This is pass. So we want to train our algorithm. Classification algorithm is going to be trained using this data set. That is, this is the inputs. This is the input, which we call attribute. We also call it attribute. We also call it feature. Some people also like to call it independent variable. Independent variable. It's the same thing. That is, this is the variable that will determine the output that we're going to have. Now, then this is the target. This is what we call target. So if the target is discrete like this, like we have fail, pass, then we call it, this is a classification problem for sure. And it is a binary classification problem, binary, because we only have two options, fail or pass, fail or pass. Now we want to build an algorithm that will study the data, the inputs, compare it with the output during training, and come up with a model that will be used to classify any data that is similar to this one. This is what we want to do here. Now, let's say we have classification algorithm here. It could be any of the classification algorithm, neural network, KNN. Now, this is after training, you expose your system to it. You say, okay, when you see 5, it is fail. The system will try to understand it. When you see 6, it is pass. It will try to come up with, it will be studying and coming up with a model which we call the hypothesis function. We explained it earlier in the introduction to machine learning videos. So the hypothesis function is being come up with. As you introduce more data, it could be changing. Initially, it could be H1, it could become H2, it could be H3. It keeps changing until you finish the data set. You want to expose the system to all your training data, then the system is done. Okay, I'm done with my training. Now you can give me unseen data before. So after training, the system will study the pattern of the input. If it is 5, it's fail. If it is 6, pass. So something unique. This is the model. This is the classifier model. This is the model it came up with. If the CS score is less than or equal to 5, then result is fail. So after you have exposed this data, the complete data set to the machine learning algorithm, it came up with this model. So you have built your model. This is not the model. The model is if the score is less than or equal to 5, then the result is fail. You, of course, you know otherwise, it is going to be pass. If you're not less than or equal to 5, then it's to be pass. And if you apply it even as human being, you will see that that is a very good model to generate. Because 9 is passing, 7 is passing, 2 is failing, 5 is failing. After 5 is no more failing. So this is what, we can easily see that and come up with this rule as human being. See? So this is what machine learning algorithm does. However, when the data becomes billions, millions, as human being, we cannot do it. And we can also do this easily because it's only one input. If the input becomes 2, maybe we have another input here. Apart from the grade, we also have the age of the student. We also have the kind of a transport the student uses to the school. Is it public transport or private car? And the more you add, the more input you add, the more features you add, the more complex the modeling is going to become. This is the idea. And that is why feature selection is usually a very important thing, as we're going to see later on. Now this is the model. This is the classifier model that has been generated. So now we have a new data that is not part of what we have here. You can see this is a new data, totally call it test query or test set. These are the test set. You need to keep it secret from your model. Now you know it's okay, since you have trained yourself, I have a student here with score 8. Can you give me the results? When you keep 8, the system will try to look at the model. Is the score coming in? Is 8 less than or equal to 5? No. If it is less, it will fail. But if it is no, the answer is pass. That is why he's saying that this guy is passing. This is how classification algorithm work. We can see that it's very simple. However, when you add more features, then the complication comes certain, as we are going to see. Let's look at this example again. So still illustrating classification task. This is the training. You have attributes. You can see here now, you have one attribute or feature, 1, 2, 3. This is the class. This is the target. We call it target class. You can see no, 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 yes, no. This is also binary classification problem. That's only 2 options, yes or no. Yeah. But then the difference now is the attribute has increased. Okay, the attribute has increased. So in that case, it becomes a little bit, because you have to study the attribute. Now, what is making this first? This is the first sample. And this attribute 1 is saying yes. The second one is saying large. This one is saying 125K. It's saying no. Why are these 3 yes, large, 125? Why are they no? This one, no, medium, 100K, no. These 2 are saying no, no, but you have different value with them. This is what your machine learning algorithm want to learn. This is the principle of learning. The algorithm want to understand. Why is it that this one is having no, this one is having medium, this one is having 100K, and the output is no? Maybe not diabetes or something like that, or it's not purchasing a house, or it's not going for the loan, as the case may be. But you can see no, small, 70K, no. Let's look at yes. Look at yes. Yes is no, just like this. It is large, just like this. However, this is 95K. It is yes. So the algorithm is trying to figure out what is unique in this attribute. Sorry, in this sample. Why is it yes? This is the idea of machine learning system. It tries to learn to understand the relationship between these 3 attributes that is making this one to be yes. Meanwhile, this one is having no, medium, 100K, but it is no. 2 things here are the same. Sorry, here, this first one, large. You can see large is here, large is here. But this is medium. This could be the underlying difference. So the system will try to see that, okay, we never have no and large. If you have no and large, and maybe the N is 95K or below that, it's going to be yes. So the system try to come up with, sometimes it get complicated, as we are going to see other examples. So this is machine learning. So compared to what you did here, you can see this one is very simple because we have only one attribute. We can easily figure out that if your score is less than or equal to 5, then you're going to fail. Otherwise, you pass. But once we have more attributes, it becomes difficult. So, but then machine learning algorithm can do that with haste. And that is why a lot of things are being done now using machine learning. Because as human beings, once the number of attributes increases, we lose count. We will not be able to follow it. So we need a system that can be able to follow irrespective of the number of features. Now we move on. So you take, this is the training set. We call this training set. You expose it to your algorithm, machine learning algorithm during the learning process. It will generate a model. See, it is called an induction. If you know induction in mathematics, machine learning is similar to induction, actually. Yeah, induction, mathematical induction. That is, you try to understand what will work for this one, that will also work for this, that will also work for this, that will also work for this. You try to adjust the equation, the rules, and whatever you want to come up with. So make sure that it works for all these data sets that you have seen during the training. That is why in inductive learning hypothesis, we said, if the data perform well on enough data, on enough training data, then it will perform on unseen data. This is the idea and the kind of principle behind machine learning. If you can be able to train your model to understand the training set successfully, then hopefully it's going to be able to work for unseen data set, which we call test set. So now, once the induction process takes place, which we call learning, we call it learning. So how does the learning take place? We need a learning algorithm, like neural network, like k-nearest neighbor, like we just mentioned them. So the outcome of this learning process is called model. I've classified this before and I will clarify it again. You see, there's a difference between machine learning algorithm. People get confused. Machine learning algorithm is different from model. See, machine learning algorithm is there by itself. It is when you add data, you add data to machine learning algorithm, make use of machine learning algorithm to learn the pattern in the data. This is what we are doing. The end result is going to be a model. See, but before you get the model, you must have a learning algorithm and you must have data set. So you have to do it appropriately, changing the parameter until the appropriate thing is done before you can. So once the model is built, so we move to the next stage, which is you now apply the model, which is now opposite of induction. We call it deduction. So since we have the model now, we have the hypothesis function H. So we now want to use this hypothesis function. Can you give me this data? No, small, 55K. I will use this hypothesis function to predict what's going to be the outcome. Should it be no, or yes, or no, or yes? So this is how classification task actually takes place. Now, so which summarizes it to the fact that classification has two-step process. The first step in the classification process is the model construction, what we call model construction. You build your model using the training set. We discussed this one in a couple of other videos. So you build the training set. I mean, you build your model using the training set for training. So, and then after that, you model usage, where you're going to make use of the model to start predicting unseen data sets. Now, so following this classification process divided into two, so we have at the first step, which is the model construction. See, look at this example here now. We have a data set from a university that categorizes professors into groups. Is he a tenure professor? So, or not, the one we call confirmed professor or academics in some other client. Is that a yes or no? This is another binary classification. So they told us here the name. Sometimes when they give you information, when you get your, this is an attribute, this is an attribute, this is an attribute, this is an attribute. But under pre-processing, this attribute is the target. We call it target attribute, yeah, or the output. During the system, when you are building a model, not all data sets that are given to you need to be used. For example, you have to look at the attribute and decide. Some attributes are not necessary for prediction. For example, the name. We're not going to use this for training. This is just the name of a person. We don't need it for training. So during pre-processing, we are going to remove it from our training data set. It's just for identification. And usually when we get data, especially for sensitive tasks like medical, we are required to remove the name. We usually request for anonymized data set. Anonymized data set is data set that you cannot trace the owner of that data set. You can't trace the patient that you are using the data set. That's why when you want to work on any medical project, you need to get the ethical approval, promising that you are going to stick to the medical profession and requirement. You don't show their picture, even their numbers, actually, their medical record number. Because if somebody gets medical record number, they can trace out the person in the hospital later to know that, oh, this person is sick or not, which is not allowed. So this is not part of what we need to discriminate. So we remove it. Now, this one is needed. Rank. If an assistant professor year and you have spent 3 years, you are not going to be tenure. This is the data set for training. Assistant professor 7 years, you are going to be tenure after 7 years. You are a full professor, you have 2 years, you are tenure. Associate 7 years, you are tenure. Assistant 6 years, no. Associate professor 3 years, no. So the system now trying to understand what is this relationship between this and the target. Then once this is the training process. During the training process, a model will be built. The model now came out with the rule, because the outcome of model building is actually a set of equations with parameters or set of rules with parameters, as the case may be. Now, this is the model generated. If the rank is equal to professor or year is greater than 6, then tenure. You can use the rule, check it out. So you can also develop your own rule. This is what our machine learning algorithm comes up with. Now, so we now take this one. This is the model construction stage. We will take it now to go to the next stage, which is where we're going to use it to predict. The second stage for the classification process, where we're going to use the model in the prediction process. So remember now we have the model already, which we call classifier or model. Because we use it for classification, we call it classifier. This is the model we built earlier. Now you have testing data set now. You can see the output is given, but we are going to hide it from the system. We will not show it to our model. So we also don't need the name, just for identification. Now you are going to give, now if I have somebody with a rank, of assistant professor and spend 2 years, the model will take it and predict for us. Is it going to be tenure or not tenure? Because already the outcome is already developed. This is the model. It's going to be using this rule, which is the hypothesis function now that has been developed after the training. And then it will check. This is the testing set. So usually we want to check our system on the testing set because we know the testing set. We know the output, but we'll keep it secret away from the model. So we don't want to check. Maybe when we check it, our model said, this guy is tenure. No, he's saying no, not tenure. He said this one is yes. He said this one is yes. He said this one is yes. It means out of 4, this is a mistake, because the answer is no. So we compute the accuracy of our model. So out of 4, there was 3/4 times 100. That is the percentage accuracy of that classification algorithm. This is why we need the testing set to judge our model that we have built, because after building your model, even if you decide to hide this one, you can hide this one and then try to check the model on the same training set, which we call the training performance. We want to check the training performance. We want to see how the model is performing on the set it has seen before. It could get 100%, it could get 99%. It's not really the ultimate. The ultimate is it performing on the new testing set that it has never seen before? Once you are done with that and your model is satisfactory, then we can then go for totally unseen data. Maybe now the university is now hiring new professors, and then they want to determine if these people should be tenure or not tenure. These are people that are new. Even the developer of the model is not aware of this new data set. But if you have trained your model enough, then it should be able to work on the unseen data. So they give us, somebody is a professor, he has spent like 4 years already. We give it to the system. Remember here, our model, if the rank is professor, or year is greater than 6, or because of or, so this one has satisfied the condition, it's a professor. Once you are a full professor, irrespective of the year, automatically you are tenured. This is why the output is this. So this is how you use the machine learning model that you have built to predict for unseen data set. And could be also other, as the case may be. Now, there could be other examples as the case may be. Let's look at this case also. So you have a case of another example, classification process also. We have model construction stage. So this is the name. Usually the name are just for identification. You don't use them as training features. So the age is youth. His income is low. What is the decision of the loan? So maybe let's say, maybe Jai's bank want to decide who to give loan to. So this could be one of their decisions. Is he youth? What is the income? Is the income low or high? You can see they classify them into, this is risky. You give loan to a youth who has low income is very risky. Middle age with high income is safe. So you can see, this is what we want to see. So based on that, there could be other parameters. You see, the salary, apart from income, what is the kind of personality? Does he have a recommender? So many other questions could be asked because we want to have a system that can predict with very high accuracy on unseen data set. So once we give this kind of data set, we train our model using appropriate classification algorithm. This is what we arrive at. You can see that it's getting complicated. This is the rule that is going to represent our model now. This is the model that we have developed. If the age is youth, then loan decision is risky. If income is high, sometimes you have multiple rules to deal with it, depending on the problem we are solving. So once you have done that, the classification model is there already, which is the model we already built. Then you need to make use of it appropriately to now decide what am I going to do. Now, new customers are given for you in the testing set. It's a senior, it has low income. This is the outputs. We hide it because this is the testing set. We try to check. Can you tell me if I have a senior with low income, is it safe or risky? The system will predict because you already have classification rules as your model or hypothesis function. It will predict for you to take a decision. Once we check it and we are okay that, oh, our testing set is excellent, maybe out of 50, there was only one mistake. That's going to be 49 over 50 times 100. That's very high accuracy. And other evaluation measure we already discussed in our previous videos on how to evaluate machine learning models. Once you are done, then you have a totally new data set. This data is not part of the training set, it's not part of testing set. Maybe it's just coming from the client, or you kept it so studied like validation set separately. So the new data is coming, they give you the middle age is low. What is the loan decision? You are asking, what is the loan decision? Is it risky or not risky? You can see now there, this guy is middle age with low decision. The system is saying risky. They'll give loan because it's very risky. So we use this. This is, for example, financial application. You can have so many application areas that we can decide to apply this concept. Now, we say we're going to have type of learner. So we have seen how classification model could be built, which is data plus the appropriate algorithm will give you the outcome, the model. So which algorithm am I going to use? And why should I use a particular algorithm? Which one is better considering some of these examples we have given? So inshallah, this is going to be the import at beginning of our lecture for next week. So we're going to look into type of learner. Generally, learners are divided into eager learner and lazy learner. Yeah, some are very eager to learn, while some are referred to as lazy learner. They have their pros and the cons. So which one should I go for? And at the proper time, which one is better? So by next week, by the grace of God, we are going to be looking into that. So thank you very much for listening and for the attendance, and wish us all the best. So we're going to take a couple of questions before we call it a day. Thank you.